Episode 3. Iroha loves strings. Let's recap the problem statement. We are given n strings as I and number k. We want to choose a subsequence of our strings and concatenate them in original order. We want to get a string of length exactly k, and among those we want to find lexicographical minimum. N is up to 2000, k is up to 10,000. And sum of lengths of strings is up to 1,000,000, but that's just because input size can be much bigger than that. Some examples on the left. Not much more to say. Note that it would be cool to start with a lot of A's, but we cannot get length 5 if we do that, so we have to take one string of length 2 and one string of length 3, and again all will be great, but since we have to concatenate the strings in the same order, the only string of length 3 is this one, so if we choose those two, we will start with n, which is worse than choosing a string that starts with c. But if we add another string of length 3 after all, we can start with it. The problem looks like a knapsack, and basically it is exactly a knapsack under some understanding how we comparing strings and summing up strings. So if we want to construct a correspondence to a knapsack problem, the weight of an item would be the length of the string, and the cost is the string itself. And we want to choose some subset with fixed weight and minimum cost. Like maximum cost, it's the same thing. The problem is that the cost of a set is not a sum of costs, but the sum, but for strings. So it's the concatenation. So the order matters, and it's not very clear what to do, but we still can do DP that solves knapsack, right? We can still do, for knapsack we will do DP from prefix and current weight into best cost, and since our weight is length, we will do DP prefix and current length into lexicographical minimum string of that length, because that's what best cost is. This dynamic programming has of nk states and of nk transitions. So did we solve the problem? Well, not really, because the values are not numbers, the values are strings. So we need of k memory to store them and of k time to compare them. So to just implement this dynamic programming, we would need of nk square time and memory. But this problem looks a lot like knapsack, and when the problem looks like a harder version of some problem, probably you can't do better than the best known solution for that problem. So The only way we can solve knapsack is to do some kind of dynamic programming with current total weight in the state, because we know that knapsack uh, with unbounded weights is NP complete. And well, we can't just forget about strings, but we can construct an instance corresponding to a subset sum instance. So if we are given a subset sum, or like some variation of knapsack instance like this, given an array of weights, and the question is it possible to choose a subset with sum exactly k? That's subset sum problem. And we can construct a corresponding instance of our problem. Basically, take strings of given length just consisting of letter A, and if it is possible to choose a subset with some k, we would be able to just take corresponding strings, and their concatenation will have length exactly k, and it's all just letters A, which is the best possible. And we will add a string of k letters B in the beginning, so that if there is no solution, we would have to take this string, and so the result will be just string of k letters B. So from the answer to our problem, we can understand what was the solution to the subset sum instance. So solving our problem cannot be easier than solving this subset sum instance. So it looks like we have to do knapsack, and it looks like we have to do this DP we described earlier. That means that we need to somehow solve those two issues we had. The first issue is that we need a lot of memory, so each DP state requires of k memory, and the second issue is that comparison of those DP values also takes linear time. Okay, let's try to understand something about our problem. We can solve subset sum instance on length of nk is okay for us. Moreover, we can solve the subset sum right to left and just store the whole DP table. Thus, we will understand which length we can choose for each suffix. So suppose we have processed some prefix of the strings, then on the corresponding suffix we know what length we can get. So if we are looking at some DP state, which is prefix and length, we know if it is at all possible to choose the remaining length on the suffix. And if it is not possible, we can just ignore those states, because it is impossible to update the answer using them. So we don't have to make transitions from them, we don't even have to make transitions to them. They're totally useless. We can just ignore their existence. That's cool, but it's not hard to construct a case where most of the states are not useless. You can just have a lot of short strings, and more or less all of the lengths will be reachable. But maybe we can somehow differently understand if any other states are useless. A state will be useless if anything we can get from it, like in the end, any solution we can get starting from it, is surely worse than the answer. We don't know the answer yet, but we do know something. Maybe we know that there is some string we can surely get, so the answer is not worse than that. Then if everything we can get from one of the states is worse, then that state is useless and we can just forget about it. So suppose we have two GP values. So for two states, there are some strings stored in them, and their LCP, longest common prefix, is shorter than both strings. So we have equal, 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 but then not equal letters. And we know that both of those states are not useless in the previous sense. So it is possible to choose something on the suffix to end with correct length, with length k. So what I want to say is that this first state is useless then, because anything we can get starting from that state, like we can only change this suffix, but anything we can get from the second state will be better, will be lexicographically smaller, because lexicographical comparison will look at this position, and this position is already fixed. So we know that however we will continue the second string and however we will continue the first string, the first will be worse, so lexicographically bigger. So we can just ignore it. So for fixed prefix, we have marked some states as just totally bad because we cannot get length k in the end. And we can also mark some states as bad because they are surely worse than some answer we can get. But what about good states? It still can be a lot of states. But we know that they are not yet comparable. So the shorter one is a prefix of the longer one. And that is true for any pair of good states. So if we take the longest of them, everything will be its prefix. So all the good states should be prefixes of the longest good state for given prefix, like in the GP table. So instead of storing a string for every reachable state, like first we said that we do not want to store anything at all for the states from which we cannot reach the end. Then we said that we will also ignore states that are strictly worse than some other states we have. And for all good states, we can just store this one string and the set of lengths that are good. Then corresponding kind of imaginary strings that correspond to those GP states are prefixes of given lengths of this long string that we actually store. So now, instead of actually storing lexigraphically minimum string with given length, we will store one string with length at most k and a Boolean array which lengths are good. Alright, that's of nk memory, because for each prefix of which there are, or of n, we now store one string of length at most k and a Boolean array of length k plus 1 maybe. That's great. So we have solved the first issue. The second issue is that comparisons are slow. We have to compare strings to understand which transitions to make. And yeah, comparison of strings is slow, takes linear time. But we now understand that all the strings we want to compare have kind of special structure. So suppose we are doing the transition. So we were staying at prefix I and we want to recalculate dp for all lengths for prefix I plus 1. So from each valid state, we can either just leave it be, or we can take string si and concatenate it in the back of our current string. So all the strings we will be considering are either just prefixes of di, because that's how our dp values look like, or it's a prefix of di plus we concatenated si in the back. And we want to compare pairs of strings of this type, like one of these types. Technically, there are more different cases, but the idea is the following: like, we want to compare prefix of di with prefix of di, maybe of different lengths, with si added in the back, and two different prefixes of di with si. To compare two strings lexigraphically, we want to find the first position which is different. But since we know that those blue parts are just prefixes of di, we know that they're equal. So like, this part is equal to this part, and this part is equal to this part. So the first different position should be on the right from that place, surely. Finding first different position is the same as finding longest common prefix. So like, how many symbols from the start are the same. And if we again look at this, we know that we should skip this first part, and then like, from this point we want to solve longest common prefix of si, here it is, and some part of prefix of di, so it's like just some substring of di. Moreover, if we just continue di mentally, it's still fine if we just solve longest common prefix for si and like this whole suffix of di. And it's actually similar in this case. First we want to solve LCP like starting from this position, and that's basically the same as it was here. And if LCP is smaller than this length, then we will find first different position. Otherwise we will say, okay, so these parts are also equal. Now we want to solve LCP for SI and a suffix of SI. Okay, cool. So all our queries kind of are find LCP of whole SI and either some suffix of DI or some suffix of SI. Or we can just say that it is a suffix of SI plus DI. And we need to answer constant number of such queries. Just one here or two in this case. So let's look at this string concatenation of SI and DI in this order now. Basically, for our queries is for a suffix of the string, calculate longest common prefix with this whole string. Well, we only need with CI, but this whole string is also good. We will be able to calculate what we want. But that's the definition of that function. Like for a given string, for every suffix, calculate longest common prefix with whole string. So if we calculate that function for this string, we will be able to answer queries in constant time. That function can be calculated in linear time from length, and length of DI is k, and length of SI is at most k. So for every prefix, we need to calculate that function in linear time, then do some updates, and now we can compare strings in constant time, and thus we will be able to recalculate our dynamic programming, and we get a solution in of nk time and memory. That's it for episode 3. Just a cool problem, cool application of knapsack, or like extension of knapsack. Thanks for watching.